So now we've gone up to a sixth power in our series of increasing powers of sine x as an integral, and things are actually going to get progressively more difficult from here on because it's an even power, so we can't use the substitution method, and actually becomes real problematic when we start using sine squared cubed and using double angle identities, because the thing will expand and expand. So we need another avenue of attack, and this is where further maths comes in. So there's two different methods here. First one I'm going to use is the de Moivre's theorem substitution or identity. I'm not going to derive it, but I'm just going to state it at this point. So we can use the de Moivre's identity that z to the n minus 1 over z to the n is equivalent to 2i sine theta, okay, or sine x in this case. So what we can effectively do is rearrange that, and we can say that sine x is the same as z to the 1 minus 1 over z to the 1 multiplied by 2i in the front, or I can say that sine x is equivalent to 1 over 2i brackets z minus 1 over z. So if I was to raise that to the power of 6, as in our integral, I would have to raise everything to the power of 6. So it would be the whole thing to the power of 6. So I'm going to deal with the 1 over 2i to the 6 first. So 1 over 2i to the power of 6 is just 1 to the 6 over 2 to the 6 I to the 6. So that becomes equal to 1 over 2 to the power of 6 is 64. And I to the power of 6 is the same as I squared cubed. Now I squared by definition is negative 1. If I cube that, I get negative 1. So that becomes equal to negative 1 over 64. So that's dealt with the multiplier outside of the brackets. What we're going to have to do now is deal with everything inside the square brackets, the z minus 1 over z. So I'm going to do that on the left hand side. So we have z minus 1 over z to the power of 6. Now I tend to use, for the coefficients of these binomial expansions, I tend to use Pascal's triangle because it's quite easy to structure. So I've got 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And if I keep moving down, I need to stop when there are 7 coefficients, or 7 numbers, because we're going to get 7 terms. So it's 1, 4, 6, 4, 1. So we're on 5 at the moment. 1, 5, 10, 10, 5, 1. And then we get 1, 6, 15, 20, 15, 6, and 1. So the last row of Pascal's triangle I've written down are my coefficients. Okay, so I'm going to write those over here so I can keep track of them. 1, 6, 15, 20, 15, 6, and 1. So those are my binomial coefficients. I'll rub everything else out to give myself a little bit more room. So expanding my z minus 1 over z to the power of 6, I end up with 1 times z to the 6 plus 6 times z to the 5, and that becomes negative 1 over z to the 1, plus, so I'm going to need all of my space over here because this is going to get big. Okay, so that's z to the power of 1, plus, so that's 1 and 6, 15 z to the 4, negative 1 over z squared, plus 20 z to the 3, negative 1 over z, so 3 there, to the 3, and then we got plus 15 z squared, negative 1 over z to the 4, plus Oops, that doesn't look like a Z. Okay, we're nearly there. Plus 6Z negative 1 over Z to the 5. And then we've got, and I know it's going to be plus Z to the 6 because it's an even power. Well, 1 over Z to the 6 rather. Okay, so if I simplify that, so I'm going to be effectively dividing my powers of Z and Z squared and so on. And I'll also notice that the signs flip. So Z to the 6 is positive. This next one is going to be subtract 6Z to the 5 over Z, so that becomes Z to the 4. And then this next one's positive. And then we end up with 15Z squared. Next one's going to be negative. The Z cubed over Z cubed simply cancels, so we end up subtract 20. And then we're over here now, so it's going to be plus 15 times 1 over Z squared. Okay, and then the next term is going to be minus 6 over Z to the 4, or 6 times 1 over Z to the 4, and then finally I get plus 1 over Z to the 6. So why is that useful? Well, you'll notice that we have pairs. We've got Z to the 6 and 1 over Z to the 6. Okay, and we're going to pair things up. I can also see that I've got minus 6Z to the 4 minus 6 times 1 over Z to the 4, and then we've got the final pair, which is plus 15Z squared plus 15 times 1 over Z squared. And then finally we've got constant term, subtract 20. So we can now sort of take out factors. We don't need to take out a factor here, we can leave that as it is, Z to the 6 plus 1 over Z to the 6. And then here we've got subtract, and I'm going to put in brackets, oops, subtract, there's a common factor of 6, brackets, Z to the 4, because this is negative, this will become positive inside, so 1 over Z to the 4, and then we've got plus 15 Z squared plus 1 over Z squared, then we've got minus 20. Okay, so I'm going to move on to my second board and continue with my integration when I finally get there. So just a quick reminder where we're at. We've rewritten sine to the power of 6x as equivalent to negative 1 over 64 multiplied by everything on the right hand side from Demoivre's theorem. It looks a bit messy at the moment, but we're going to use another fact, another one of Demoivre's identities actually. So I'm going to use the fact that 2 cos nx is equivalent to z to the n plus 1 over z to the n. And you can probably see that we have lots of repetitions of that inside the square brackets. So we can also say that, for example, z to the 6 plus 1 over z to the 6 is equivalent to 2 cos 6x. Okay, so if we use that fact, we can put 2 cos 6x in place of z to the 6 plus 1 over 6 z to the 6, and we can also do that term by term. So sine to the 6x now becomes equivalent to negative 1 over 64 still out in front, and then inside we've got 2 cos 6x minus 6 times 2 cos 4x, because the power is now 4 for the second term, and then we've got plus 15 times, in this case it's 2 cos 2x, and then we've still got our minus 20 at the end, a little bit of a squeeze. Actually, I'll just make that a little clearer. So we've got 15 times 2 cos 2x minus 20. Okay, so we can now multiply that through and we can go ahead and perform our integral. Okay, so how I would do this actually would be to have my integral now, which is what we had at the top. So the integral of sine 6x is in fact going to be equivalent to negative 1 over 64 times the integral of 2 cos 6x minus 12 cos 4x plus 30 cos 2x minus 20 dx. Again, I keep running out of room at the end here, as is to be expected with such a long integral. Okay, so let's finish this off, shall we? So we're going to get negative 1 over 64 times inside. Sine differentiates to cos, so cos integrates back to sine with no change of sign. So it becomes 2 over 6, 2 over the 6 in front of the 6x. So it becomes a third sine 6x. The next one becomes negative 12 over 4, so in fact it becomes 3 sine 4x. And the next one becomes 30 over 2, so it's plus 15 sine 2x. And then at the end it's just minus 20x. Okay, so what we can now do is simplify that yet further, which might happen on my bottom line just about. Okay, so we end up with 3 times 64 is 192, so it's negative 1 over 192 sine 6x. The next one's going to be positive 3 over 64. I cannot simplify that. Sine 4x. And then the next one is going to be minus 15 over 64. Once again, doesn't simplify. Sine 2x. And then finally we've got plus 20 over 64, 10 over 32, 5/16 x. Okay, I'm not going to put my plus c in because it won't fit. Okay, so that obviously is a lengthy process, but it's quite formulaic, and it is a very sort of valuable skill in further maths, and certainly one that you can be examined on. Thank you.